Check it out now, y'all.
nanoHUB-U online instruction.
Welcome back. This is the fourth lecture of week 5 on the material science of rechargeable batteries. Today we're going to talk about porous electrode theory. This is the theory that people use the most to describe the kinetics, the transport in rechargeable lithium-ion batteries. Really, what it boils down to is on the description of mass transport across volume element of material. And conceptually, what you have is the transport, how much mass enters one phase of, I'll say, if you consider a cube of material, that being the electrolyte or that being a active material where you put charge, okay? And on one side, you have a certain amount of flux that enters at a distance dx over 2 away, and at the same time, a fraction of it exits the other side of the box. So if you go over the math as to that the mass that accumulates in this bit depends on the size of this element and take it to the differential limit, you will find what I refer to as the charge accumulation equation, where basically the amount of charge stored in that volume element depends on the minus the divergence of the charge flux. Think of this term J sub rho as basically the current density, the number of coulombs per meter per second that are entering this bit. Okay, while you can also count if you have n species for the ith species, we can also say that that much mass is entering this bit or accumulating in that bit. Okay, really what we're saying here is that whatever comes in the box, it's accounted for, that we do not create or destroy any mass. Okay, and these equations are very general to describing the transport of any system. They have been used not only, of course, for batteries, but for the description of any type of multi-component ionic system. And notice here that I left very open what the current J sub rho or the mass flux J sub I is. Okay, we really would like to define this function, but as you can imagine, right, trying to define a flux that is a function of composition gradients, that is a function of charge gradients, that is a function of thermal gradients, and whatever deviation from equilibrium driving force that impacts on the accumulation of mass will lead you to have to redefine what that flux J sub rho or J sub I are. To a first approximation, say for example, if you consider the flux being a linear combination or a function of all the possible driving forces, in this case J sub Q, you can think of it as the heat flux. So the heat flux depends on the driving force for heat, which you can think of it as the thermal difference. F sub rho, which is the driving force for moving charge, and F sub 1 to F sub n, which corresponds to the driving forces for moving mass. Okay, if you assume for small deviations from equilibrium for that flux, then you can think of that those small deviations can be expanded in terms of a Taylor series, and here is where things get really messy, because now we're really thinking that there's a whole set of linear combination of driving forces that impacts the response of the system. This description, this mathematical description of the fluxes can always be resolved by using something called irreversible thermodynamics, and in this case it boils down to the identification of what each of these coefficients, these partial derivatives, means. There are some rules, a very well specified set of rules as to what controls it, but as you can see, it all depends on what the linear driving forces specify the control of it. And here the key word is that we are performing small deviations with respect to the equilibrium value. Okay, if we had large deviations, then we will not only have to put the linear terms, but we will have to include the quadratic, cubic, higher order contributions to the flux of the system. But in the limit of small deviations, then we can think of these combinations. There are some specific rules associated with this, such as that this coefficient has to be numerically equal to that coefficient, and if we put all these coefficients in a matrix, the determinant of the matrix has to be positive. Why? Because overall, there's a requirement for the entropy of the system to increase or remain fixed as mass and different fluxes occur. So really, what do these driving forces that we have, these F sub I, okay, some of them we already know them. For example, you can think of them that for heat, the main driving force really corresponds to the gradient of temperature, and we know this one very well. We know it as Fick's second law, okay, first or second law. We then have mass transport, which in this case we know that the driving force is as we have learned during these weeks, corresponds to the gradients of chemical potential. Okay, and if we do that, then we get also Fick's law when it comes to mass transport. And similarly, for charge transport, we know that the voltage gradients are the driving force for charge moving from one direction to the other one. So this is known as Ohm's law, which basically we're saying that the gradients of voltage are proportional to charge fluxes, where kappa in this case corresponds to the conductivity, right? And we've known that, right? So now, what I was saying regarding the coefficients, the requirements for those coefficients is as if we put them in a matrix, then the coefficients have to be numerically equivalent, okay? And as we put them in a matrix, the determinant of those coefficients has to be positive, so that the entropy, the heat that is generated, leads to a total amount of entropy that increases, so that we can satisfy the second law of thermodynamics, and that is known as Onsager symmetry principle, as we describe now. This is sounds very theoretical, very abstract. What you really want to do ultimately is write these driving forces in terms of equations of this form. Okay, you can see this is more manageable now, because now I have that my charge flux is proportional to the gradient of the chemical potential. Okay, and in the case of a battery, right, it is that chemical potential difference or electrochemical potential difference, if I bundle these two, the ones that is driving mass flux from one electrode to the other one. But as a result of this fundamental description, we also get additional driving forces because of the chemical potential gradients that are for the other species, right? So in this case, you can think of it as having the first term being the diffusion term, as we have known it in the past before, right, where the mass flux is a result of the gradients of chemical potential. But now, people refer really to this point as the electromigration contribution, unless of course you rearrange these terms and define a variable eta, so that mu1 plus zf phi gives you that over potential, and then you can think of that whole thing as an over potential, or as a electrochemical potential driving the system in one direction, right? And well, then you will also have these osmotic pressures, or you prefer a chemical wind term, where the diffusion of another species could be in a completely different direction, could be driving the system to flow in a different direction, just as a matter of from the point of view of getting the flux right. Now, you do this for every single contribution, right? So at the end, you can think of every single mass flux could be written in this way, provided that, of course, your species is charged and that you have more than one species that is diffusing. So in the limit of n species, well, you can see all of them in this case become coupled and related to each other, so that the mij term would be effectively the mji term for another term over here, which will be somewhere down here, right? And overall, you can see how a chemical potential of difference of one component may induce flux from all the other components, which could be very possible in the case of systems that have multiple salts or multiple species that are diffusing, especially in the electrolyte. Now, I also want to talk about this formally. Okay, the conductivity associated to the transport of charge, okay, can be thought of as the linear superposition of all the different conductivities from all the different species, okay, as it's referred to here through the Nernst-Einstein equation, where in this case, the conductivity of the ith species is related to its diffusivity through this relationship. And as you can see, it's also proportional to how the valence of that ionic species contributes to the mass transport. And based on that, you can define effectively that the transference number as the ratio of the contribution to that conductivity divided by the total conductivity of the system. So the effective charge would really be a function of how these species are flowing in different directions, and how the chemical contributions are either driving it back if Z sub I is positive, or driving it forward if Z sub I is negative, right? It really depends on the sign of this, and it can accelerate or favor transport from one side to the other one, or it can really try to slow it down to the point of completely stopping it. Okay, now in this case you can think of this term as it's known as the conductivity term, as it's classically defined, and the electromigration coefficients really would correspond to these other terms as we've known them also in the past. And in this case, these terms are exactly the ones you saw in the previous slide of that relate to the mass transport to the voltage difference. So for an electrically charged system, you can see how this term over here, okay, even if you have only an electrical potential, that was enough to induce a mass flux in one direction and completely changing your charge flux in the medium where you have an ionic species. Now, this would correspond and would allow us to describe explicitly the mass transport in a general electrochemical system. The problem with this description is really that we have a topologically complex structure, right? I mean, as we have described, really the particles are not necessarily uniformly distributed, their shape are not necessarily spherical. We have this distribution of pores through which lithium has to be diffusing through, as you can see here, right? And in addition to that, we will have to specify properties for each phase, for each section, both on the anode and cathode, some properties to the separator itself. So really this becomes an unmanageable task if you wanted to do this in the comfort of, say, your PC only, right? You can solve this numerically, of course, if you want to run massive calculations in computer clusters, but in many cases what we want is just to understand the details of what happens in one specific structure. So because we have been describing the structures in terms of their thickness under porosity as it's done in industry, the way to tackle it is simply by trying to divide the problem into its most elementary pieces. So you can think of having, again, this very complicated system where every single phase can have very different properties, and instead say, well, I'm going to divide this problem into two parts. I'm going to assume I have the electrolyte part alone, okay, where basically I'm looking only for what happens between the particles and understand the transport by assuming that the ions are charged and that there's a path for those electrons to flow through the different species, okay? And on top of that, I am going to replace all the particles inside the anode by a representative particle that allows me to describe the transport through that layer. Okay, and in the cathode side, I can do the same thing. I'm going to average out the properties of the topology associated with the cathode itself, and instead I'm going to replace it by a representative particle that I can put as a test particle in every spot, just to be able to describe the lithium accumulation inside that specific material. Now, if I do that, then because of the symmetry of the problem, you can define a line, basically the diffusion along basically from anode to cathode in one dimension. If I have homogenized the properties, I don't need to look what happens out of the plane or in the vertical direction. I only need to describe the transport along the x-axis. So if we do that, well, then I can define then the lithium transport in the electrolyte across a one-dimensional domain where I can always exchange lithium from the electrolyte into the particle via the Butler-Bowman relationship by defining some average reactivity. And in this case, I would have to solve, of course, for the transport inside one particle, but I can always exchange that at every single spot in the anode itself. And I can do the exact same thing in the cathode side, and well, you can think of it as that when the battery starts to discharge, basically this representative particle exudes lithium dumps lithium into the electrolyte. That diffuses through those electrochemical equations that we just described, okay, and then it through those electrochemical gradients, then we have mass transport, in this case in the anode section and in the cathode section, and the cathode particles basically will take that lithium back in, allowing us basically to decouple the problem into two parts. One where we have the transport in the electrolyte alone, okay, where the properties will be basically just position dependent in those three layers, and the diffusion from the electrolyte into the cathode by defining a representative particle on each phase. How do we specify the reactivity of each of those structures? We already discussed this, and in this case, the reactivity of the anode is proportional to the porosity associated to the anode divided by the particle size, as we have described, and the reactivity of the cathode has a similar relationship, except of course that we have different porosities that we have tuned based on how much is the theoretical energy density that we want on each of those layers and what particle size we have in order to balance out the capacity ratio. So, and of course, we have also that in the anode side, we have a different Butler-Brommer relationship than the cathode. And as we have also described in previous weeks, the reactivity on this side per particle could be very different than the reactivity per particle in the cathode, giving you a completely different dimension as to how to describe this. So now if we do this, then we have to recast transport in the electrolyte. We have to describe it separately, because even though transport within one particle is very well known through the boundary condition at the particle electrolyte interface, in the electrolyte, now we have to account for the mass associated to the accumulation that only occurs, as you can see here, through the porosity, and say, well, that corresponds really to the lithium in the electrolyte, and I have to account for the lithium that I actually take away from the electrolyte, and put it or remove it from the particles. Okay, those two contributions allows me to see how lithium diffuses through the porous electrode, and how there is an intake with the electrode materials. And mathematically, that is represented by this mass flux. Basically, you can see it looks just like a fixed first and second law statements. However, the lithium exchange with the particles is defined in this case by the Butler-Brommer relationship that you will always have at every point, okay, times the area that the particles expose per unit volume, just like we were describing in previous lectures, okay. And if you do that, well, you can always do it, of course, for every single contribution. You can change this reaction and that area per unit volume for both anode and cathode. You can make it position dependent, and if you do that, then you will have a very reasonable description as to what happens in the system. And of course, in this case, you know that your mass flux will be effectively, in this case, a function of the voltage gradients and the concentration based on the descriptions that we just provided. However, this D tilde and L tilde really corresponds to the microstructurally average properties as defined through the different electrodes. This means that we have to now include the tortuosity associated to a system, and as we have defined before, that is given, in this case, the average diffusivity is given by the porosity times the diffusivity in the electrolyte divided by the tortuosity. If we assume that this tortuosity is of Brugman type, then we have this very simple relationship that we can put in there, and we can do the same for every single other property. And of course, this assumes that all the transport is occurring between the particles in the particle interstices. And if this doesn't happen, if instead the transport also occurs within the particles, okay, then we have to go and revisit that equation. Now, we will have something very similar for the charge accumulation. In this case, we have the same idea, except that in this case, charge occurs at steady state. Okay, where we have to account now for the charge accumulated in the electrolyte and the charge that is actually being exchanged with the particles as a result of the discharge or recharge of the cell. Okay, mathematically it's written the exact same way. You can see we have that the charge accumulation is going to be in this case related to how much charge has been reacted per unit volume in each of those particles, and is in this case is the exact same idea. That charge in the electrolyte would correspond to this relationship, and the other term corresponds to basically the Butler-Bowman relationship as we have defined it. However, in this case, the conductivity is also going to be a function of the voltage and the concentration gradients, and we have again the same type of relationships where now the conductivity is, if we consider of Rutschmann type this porous electrode, we have the exact same relationship where the conductivity goes as epsilon kappa over tau, and we get the same type of relationship. So now that's of course in the electrolyte phase where we have the particles, okay? But we still have to solve for what happens in one particle. And in this case, if we look at my one representative particle, the mass transport equation still applies, and because the mass that is diffusing through is not charged, we have the simplest, basically we have the simplest diffusivity associated to the system, where now we have this Neumann type boundary condition, we have this flux boundary condition at the interface, which really is a function of the overpotential and what is the charge accumulated at the surface. And the bulk of it, we really have this relationship for the flux, where basically it really goes downhill, in this case from the top to the inside, of course, unless there are phase transformations occurring. And this really completes the description, because then this means that we can totally have this description where we have both anode and cathode and use the relationships that we have described, right, where we have the reactivity and the tortuosity associated to each of the phases. Externally what we have is that we would like really to have the system chemically insulated. So numerically what you do here is on one side you put a boundary condition where you enforce that no mass can be extracted from your battery. And of course in a real battery that would mean that you're saying no leaks. Okay, you're saying also that that's a very well chemically insulated cell, and you also say that you have in this case charge that is being extracted from the anode and put it on the other side. So for the mass transport equations you specify the chemical insulation boundary conditions, and for the charge continuity equation you specify this type of boundary condition, and the rest is just iterating over these equations as it has been done for many years by Newman and co-workers. Okay, that corresponds of course to those boundary conditions at that interface. And if you do that, if you agree with this, you can also not have to necessarily solve the entire electrode, the entire anode separator cathode system, but if for every ion, for every electron that is moving in that direction, there's an ion, a positive ion that is going out from the anode into the cathode, so you can not necessarily have to solve the whole thing, but focus on solving only for half of the structure, where in this case these two boundary conditions are the same, except that now you are assuming that on this side you put an ionic charge boundary condition as a result of the ions moving in this direction, and you ground it so that you can look at not an overall cell, but at half the cell, which is what many people do if they're trying to engineer the electrode of the system. It is not surprising then that if I make my electrode thicker and make a very low porosity, I should be getting the same type of response as before. Now, this is very important. What are the assumptions that we're using to describe the system? Because if we don't get the assumptions right, we will not really be solving for the right problem. So in this case, porous electrode theory assumes, as you have seen from the previous slides, that particles are perfectly spherical monodispersed units. We know what are the implications for that assumption in the case of real batteries. Okay, we are also, because we are only solving for a representative particle, we're assuming that particle-particle interactions are negligible and only occur through the electrolyte itself. Okay, basically the particle interacts with the electrolyte at one spot, and in the next spot the lithium distribution is going to be impacted by what happened in the previous particle, and that will impact what happens in that particle itself, but that particle will not see what happened on the neighboring particle. Now, there's a big assumption that every position along the electrode thickness is microstructurally equivalent, okay, which means that we have uniform porosity, which, as you know, as we have learned, is not necessarily true. We have uniform electrical conductivity, okay, as we know, you can have clumps of particles and open spaces that will impact on the performance, and we're assuming uniform diffusivity, okay, which also might not be necessarily true. Finally, we also are making an assumptions of the conductivity and diffusivity in the electrolyte are much larger than in the active material. If this is not true, if this were not true because, say, you discover a material whose conductivity in the particles is much larger, then you would have really to recast the whole equations and not use the Bridgman relationship as it is, okay? And the transport pathways, there will always be transport pathways for both electrons and lithium ions to get to every single spot. It's a very important assumption because as we have also learned, if the particles and the electrolytes and binders are not well mixed, what we will get is that you could have very isolated regions and regions that become very conductive. Now, this model was implemented by Newman, and he has worked on it since the 60s, and he has done a great job. This is for half a cell. You can see how the lithium distribution in the electrolyte as a function of position. This is the anode, this is the separator, and that's the cathode. And you can see how, as the discharge proceeds, the carbon side of the cell, the anode side, is exuding lithium into the electrolyte. That's why it differs. It basically, you have an excess of lithium in that area. And as a result of that, as compared to the initial state of 1 mole per decimeter cubed per liter, it's flat at the beginning. You basically can double it, and in the back, because we're taking lithium from the electrode and putting it into the particle, the concentration drops all the way to the point in which it actually can drop to 0. For a 1C structure, a 1cc rate, you can see how, depending on how fast you go, for different instants, you can deplete different parts. Why? Because the front of the electrode can become more opposing more transport as the discharge proceeds, and there could be cases where the potential, basically, well, as one would expect, in the separator side is flat, but it varies non-linearly as you go to the back as a result of the charge that you're removing and putting into the particles. In both cases, well, in one case, the exuding lithium into the electrolyte results in that lithium accumulation, while electrically it means to the creation of charge as that charge is being put out into the electrolyte and being taken in the cathode side. If you do this at different C rates, it's not at 1C, but say 3C, that accumulation can be very large in the anode and basically will be a result of the tortuosity that will oppose transport for lithium from the back of the anode into the cathode. And in the cathode itself, you can really get very fast to completely deplete the cathode of lithium as a result of that lithium cannot reach so fast the back of the cathode. And at 5C, of course, it only takes, as compared to 3C, where after 11 minutes, we're very close to the end of the discharge. After 4 minutes in 5C, basically this battery is completely dead. Okay, this really gives us the opportunity to define something called a diffusion ratio, which is how much will those diffusion limitations will take place, which corresponds to taking the ratio between the diffusion time to the discharge time. And we can readily define this by taking the the particle size squared divided by the diffusivity, or comparing the discharge time to the total charge of the system divided by the current. So if you do that, what you will get is a very nice number that gives you an order of magnitude as to when diffusion could be limiting the transport on the system. Okay, so for example, for a C/2 discharge of lithium in a graphite particle, you can see that after 63 minutes, the concentration gradients are very shallow as a result of the fact that the diffusivity of the cathode particles is very large. And so you would have to go through great lengths to have to increase the C rate to actually see that concentration drop significantly in the system. At the end of the day, what we care, however, is on what the macroscopic voltage of the cell is. So you can see here how for 3 milliamps per centimeter square discharge, you can get one type of response, but as the C rate increases from that number to 4 or 5, the voltage will drop as a result of these transport limitations that occur in the cell. The concentration will play a very important role, the initial concentration in the electrolyte, and you can see how by changing the initial concentration from 1.4 to 1.2 and 1.1, you can deplete what you have accumulated in the electrolyte sooner, dropping without the response of the system. Now, some of you may be asking, how does this relate to the reaction zone model that we talked about a couple of classes ago? Well, if you plot the reaction rate as a function of position for different instants, what you will find is that, say, after 8 minutes, all the reaction will occur in the part of the cathode that is the closest to the anode. So you can see all the reaction is occurring here. Okay, in this case after 8 minutes. If you do it after 18 minutes, notice how all the reaction is basically focused on one region in the cathode, really defining this strip of material being the one that is electrochemically active. Similarly, after 36 minutes, that boundary has migrated further deeper into the cathode, and after 55 minutes, you can see here how, basically it has reached the back. So effectively, numerically, the system actually indeed captures this transport, you have this boundary region, this reaction zone that is moving to the back, capturing it very well. Okay, and if you have that, it's interesting to see how the second peak develops, and at the very end, a part of the material recovered, so you get an extra peak back, which is something you will not see using the reaction. So, but you can see how by using these type of tools, these type of thinking tools, you can effectively be able to design the structure and how that the reaction zone model indeed allows us to at least think about it in a more rational way how a battery works. So finally, what you really care about ultimately is the capacity of the cell, right? The voltage is a function of the capacity of the cell, and the model, as you can see, works really well. You can match very well the reaction of the system, provided that you have the correct properties. This description that I just talked about is the most popular battery description in the system in this case of the community, and people have been using it for more than 20 years. It really is not going away anytime soon. It really allows you to engineer the details as to what section will control the response of the system, and to introduce all those nonlinearities that describe the response of the system. However, as you can see for the assumptions that we perform, it's very hard to include those extremes of the distribution that the system will have. Now, on the next class, I will summarize what we have learned during the week. Thank you very much.